All right, welcome. Okay, so this is section 4.5a, solving exponential equations. All right. So we are going to be solving equations that have some sort of variable term in the exponent. Okay, we want to be able to get those out of our exponent. So we're going to have two things that we want to keep in mind. We want to be able to identify how many terms are being raised to a variable exponent, and it'll almost always be one or two terms with some sort of variable exponent. All right. So first, we're going to take a look at a case where we have one term to a variable exponent. So option A is going to be to see if our bases can match. See if there's any way we can manipulate those bases so they'll end up being the same. If so, we can set those exponents equal to one another. If we can make that happen, we can set those exponents equal to one another and then just solve for x, solve for the variable. Option B is to get the term by itself and then have everything else on the other side of the equal sign. Then we will convert it into a logarithm and solve from there. So let's take a look at what these look like, something at what one of these problems looks like. Okay, so 2 to the 3x minus 7 equals 32. So option A, we want to check and see if we can make these bases match. So on the left, we have a base of 2, and on the right, we have a base of 32. So we want to ask ourselves, can we raise 32 to some exponent that will, or can we change 32 to be 2 to some exponent? In this case, we can, because 2 to the 5th power is 32. So if we leave the left side as it is, so 2 to the 3x minus 7th power equals 2 to the 5th, because 2 times 2 times 2 times 2 times 2 is 32. So 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. So 2 to the 5th power is 32. Since we have the same base, 2 and 2, we can say, okay, the only way for these two bases to be raised to exponents and they're the same is going to be if those exponents are the same. So 3x minus 7 equals 5. The bases just go away if we can make them be the same. So from here we want to solve like normal. 3x minus, or excuse me, adding 7 to both sides, we get that 3x is equal to 12. Divide both sides by 4, we get that x is equal to, or divide both sides by 3, excuse me. I'm not quite sure why I divided by 4. Divide both sides by 3, and we get that x is equal to 4. Okay? So then we can take and plug this back in to our original problem. So 3 times 4 is 12, minus 7 is 5, so 2 to the 5th power is indeed 32. So 4 works. Okay? They can be as easy as that. So try this one on your own. See if you can get those bases to match. See if you can get 5 to the 4x minus 7 to equal 5 to some exponent. And if you can, set those two exponents to equal to each other and solve for x. All right, I'm going to pause. You should do the same. So I will give you a second to pause in 3, 2, 1. And welcome back. Okay, so we could get 125 to be equal to 5 to some exponent. We could say that 125 is equal to 5 to the 3rd power. So when we have that, we take and we set these two bases equal to each other. We say these two bases are equal to each other. Therefore, the only way that this can be a true statement is if this exponent matches this exponent. So we can take and set those two exponents equal to one another. So 4x minus 7 equals 3. Add 7 to both sides again. We get that 4x equals 10. Divide both sides by 4 this time, and we get that x is equal to 10 over 4 or 5 over 2. Okay? Or if you really want to be that guy, 2.5. All right? So that is option A. Can we get the bases to match? This is kind of similar to option A, or this is option A still, but it looks a little bit different. Okay? So we want to be able to get all of our bases to be the same. We generally want to find the smallest base that we can do that with. Well, in this case, that's going to be 3. So 27 ends up being 3 cubed. And over here, 3 is our base, so 5x. But then we have 9. 9 is going to be 3 squared. So we can take 3 squared and raise that to the x squared power. Okay? And whenever you have an exponent or a base raised to 2 exponents, you multiply those exponents. So 3 cubed equals 3 to the 5x times 3 to the 2x squared. Okay? Now, here we are multiplying two bases together. So when we multiply two bases together, we add our exponents. So we have 3 equals 3 to the 2x squared plus 5x power. And now, oops, sorry, 3 cubed. 3 cubed equals 3 to the 2x squared plus 5x power. So the only way that that can happen is if these two bases are the same. Now I want to pause here. If this right here, this going from this step to this step was confusing, or if going from this step where you have these two multiplication problems to this step is confusing, please take a look back at page 10. I promise if my board would work, it would I would be able to circle that. But page 10 in your book has a bunch of exponent rules. Hi, wife. Page 10 has a bunch of exponent rules that you will be able to use and manipulate to get what you need to do, or be able to understand and figure out what you need to be doing when you encounter weird exponent-y things like this. So if you need to, please pause the video, go take a look back at page 10 and really kind of dive into why the things that just happened. Okay, but once we're back here, we can take a look and say that 3 equals 3. So in order for this to be a true statement, our exponents have to be the same. So 3 equals 2x squared plus 5x. And then since it's a quadratic, we want to get everything equal to 0. 0 equals 2x squared plus 5x minus 3. So now we need two numbers that multiply to be -6 that add to be +5. And those two numbers are whoopsie daisies, multiply to be -6, but add to be +5. Those two numbers are -1 and +6. So we can say 0 equals 2x squared. We factor this to get to -1x plus 6x minus 3. So we ask, what do these first two terms have in common? They have an x, so x times 2x minus 1. And these second two terms, what do they have in common? They have a 3 in common, so plus 3 times 2x minus 1. These two terms have a 2x minus 1 in common, so 2x minus 1 times x plus 3. And then we get that 2x minus 1 equals 0, x plus 3 equals 0, or x equals 1/2 and x equals -3. And if we plug either -1/2 or, if we plug 1/2 or -3 into our original equation, we'll find that both of those solutions do indeed work. Okay, so this is really taking and putting all together a lot of the stuff you've already been doing. Okay, and a lot of the stuff you should be able to do. Okay, so these exponent rules are new. The exponent rules are not new, but the manipulation of them is, and the trying to get them our bases equal to one another, that's new. But this right here, once you're able to get here, this is factoring. Okay, this is all factoring, and this is all stuff that we've been doing for a long time. Okay, so please again review those exponent rules on page 10, but also remember that factoring is never going to go away. We wouldn't have spent so much time on it at the very beginning of the year if it did. Okay? So, this is a slightly different example. This goes back to option B. So, because we can't get 20 to end up being any kind of exponent of 3, we want to take a look back at option B. We can't get those bases to match. So, get the term with the exponent by itself, probably should have left that in there, get the term with the variable exponent by itself, and then everything else on the other side of the equal sign. Then convert it into a logarithm and solve. So let's take a look at that. Okay, so we want to get the term with the variable exponent by itself, and then everything else on the other side. We did that. Okay, so let's turn this into a logarithm. When we turn this into a logarithm, base 3 of 20, remember, this guy goes in your base, this guy goes in your argument, equals our exponent. Well, I don't know 3 to what power is going to be 20, so this is where we want to bring in our change of base formula. So log of 20 over log of 3, I just used base 10 because there wasn't something nice that worked with both of them, is going to be our solution. It's going to be our x. So let's take a look at the calculator and figure out what we need to do. All right, so turn it on. logarithm of 20 divided by logarithm base 10 of 3. All right, so on our calculator, on our calculating machine, we have typed in exactly what we have right here. So let's go ahead and hit the old equal button, and we get 2.726 as our solution. 2.726. Okay? So 2.726, and it's like 2.7268, so let's round it up to 2.727. Why not? Why not? Let's get weird. 2.727 equals x. Okay? So use that same idea. Get the thing with the base on one side by itself, and then solve for your, rewrite it as a logarithm, and then solve for your variable. Rewrite it as a logarithm, solve for your variable. I'm going to give you some time to work on this on your own. I'm going to pause in 3, 2, 1. All right, so converting into a logarithm actually turns this into a natural log because our base is e. So we have a natural logarithm of 2500 equals our exponent, which is 0.08t. So natural log of 2500 equals 0.08t. Our goal is to get t by itself, so I divided both sides by 0.08, and then typed into the old calculator, natural log of 2500 divided by 0.08, and we got the number 97.8 and some change, but not enough to round anywhere up. So 97.8 is our value for t. All right, so we can convert to a logarithm, then use our technology and our knowledge of logarithms and how they work to help us get to a solution. Okay, so now we want to take a look at multiple terms to variable exponents, and in most cases it's going to be two terms that are going to have variable exponents. Okay, so we're going to have a process for how we want to do this. Get the terms equal to one another, so get them on opposite sides of the equal sign. Then we want to take a logarithm of both sides. Our logarithm is an operation, so if we take the logarithm of stuff that is, if we take a logarithm of two equal things, the logarithm of the left is going to be equal to the logarithm on the right. So we are allowed to do that on both sides of our equation. Then we want to use that power rule that we talked about in class about how we can take the exponent and move it out front. We want to get the variables out of the exponent using that power rule. Then if we need to, we want to distribute. We want to distribute if necessary. So then we want to get all terms with variables on one side of the equal sign and all terms and all the others on the other side of the equal sign. This will make a little more sense when we actually see it. All right. Then we want to factor out the variable. And then once we've factored out the variable from all the terms that have a variable, we want to then divide by the thing that we're multiplying the variable by. And then once we divide, we want to just eventually get to a number. Okay? So let's take a look and see what this looks like. Okay. So we have 4x to the 4 to the x plus 3 is equal to 3 to the negative x power. Okay? So what does that look like? How can we work with this? Well, let's go back to our steps. We want to get everything equal. We want to get both those terms equal to one another. Check. We did it. We're the best. Guys, we're awesome. Then we want to take the logarithm of both sides, okay? I would almost always recommend taking the common logarithm, so logarithm base 10. That will generally give you the most consistent results. You can use any logarithm you want, but I would recommend logarithm base 10. So log base 10 of 4 to the x plus 3 equals, oopsie daisies, oopsie dipsy daisies, logarithm base 10 of 3 to the negative x. Then we want to use the power rule to get all those exponents out of, or to get all those exponents down. So all those exponents are going to come out front of our logarithms. So we have x plus 3 times logarithm base 10 of 4 equals negative x times logarithm base 10 of 3. Okay, so this is what we want to look out for. If we have any sort of terms like this, where we have a bunch of stuff times our logarithm, that's where we want to distribute. Okay, so go ahead and distribute, where we have x log base 10 of 4 plus 3 times the log base 10 of 4 equals negative x log base 10 of 3. So once we distribute, we want to get all of the terms that have a variable on one side of the equal sign and all the other terms on the other side of the equal sign. So what I'm going to do is I'm going to subtract 3 log base 10 of 4 from both sides. Oops, log base 10 of 4. Okay, going to subtract that from both sides to have x log base 10 of 4 equals negative x log of 3 minus 3 log base 10 of 4. And then I'm going to add log base 10 of x log base 10 of 3 to both sides, x plus x log base 10 of 3. We're going to add that to both sides to get x log base 10 of 4 plus x log base 10 of 3 equals negative 3 log base 10 of 4. So once we're here, then we have all of our x terms on one side and all of our not x terms on the other side. So let's go ahead and factor out our x from this term, since both of these have it. X times log base 10 of 4 plus log base 10 of 3 equals negative 3 log base 10 of 4. A couple different things you can do here. You can just divide both sides by log base 10 of 4 plus log base 10 of 3. Log base 10 of 4 plus log base 10 of 3. Or you can take and convert this log base 10 of 4 plus log base 10 of 3 to log base 10 of 12, because they're added together so we can multiply in there. If you want to divide by something a little easier, feel free to convert this, but you don't have to. So once we're here, we get to x, since these reduce, x equals negative 3 log base 10 of 4 over log base 10 of 4 plus log base 10 of 3. So from here, it's some calculator work, so let's take a look and see what this number is. X equals, let's take a look and see what this number is. Oh, wake up, calculator. There you are. Hi. Okay, then we have our numerator, negative 3 times log base 10 of 4. Close the parentheses for our logarithm, and then close the parentheses for our numerator, divided by our denominator, which is log base 10 of 4 plus log base 10 of 3. Once we have those, close our denominator up, and then hit the old enter key. And we get that x is equal to negative 1.674. X equals negative 1.674. Okay, and then if you take that value and you plug it back into your original equation, you'll end up getting a true statement. Okay? So I've got one more example for you, and then feel free to go ham on your homework. So let's take a look. All right, I'm going to let you try this one. So on your own, give this a shot, and then resume, and I'll talk through the solution. All right? So I'm going to give you a chance to pause in 3, 2, 1. All right, welcome back. Hopefully you found that x was equal to negative 0.612. Let's talk through what I did. All right, so got the two things equal to one another. Good, wonderful. Took a logarithm of both sides. After I took that logarithm of both sides, moved the exponents out front. All right, since they were both two-term exponents, I had to distribute. And after distribution, I got x log 5 plus 2 logarithm of 5 equals logarithm base 10 of 4 minus x times logarithm base 4. So then, went ahead and switched, got the x terms, the variables having terms on both sides. So x logarithm base 4, negative x logarithm base 4, added it to this side, and then subtracted 2 logarithm base 5 from this side. From here, this is a lot and kind of gross, so I simplified these logarithms down into one logarithm. So logarithm base 4 minus 2 logarithm base 5. 2 logarithm base 5 is the same thing as log of 25, or 2 logarithm base 10 of 5 is the same thing as logarithm base 10 of 25, 5 squared. So with this minus sign, the 25 goes in the denominator, the 4 goes in the numerator. So we have logarithm of 4 over 25. And then we have x times logarithm of 5 times 4, which is 20. So then I divided logarithm of 4 over 25 over logarithm of 20. And as you can see on the handy-dandy calculating machine, logarithm base 4 of 25, or logarithm base 10 of 4 25ths divided by logarithm base 10 of 20 ends up being negative 0.612-ish. Okay? So that's about all the examples I have for you. So go ahead, get cracking on your homework. You got this. I believe in you. Do your best. If you need to, feel free to watch this video or roll back to the steps, the process that that we need to go through to do this. Whatever works for you, please do it, okay? I believe in you. You got this. And tomorrow we'll be solving logarithmic equations. So enjoy this and have some fun tonight, and I will see you